So we've said many times that not only is electrochemistry one of the most intriguing areas of chemistry, but it's also one of the most unifying because it brings together virtually every aspect of what we've studied so far. And to make that point, we're going to build a master diagram that connects every chapter of the book up to this point. And remember that way back in chapter 3, we developed the idea of the change in enthalpy for a reaction, and we measured that delta H, that release of enthalpy in a reaction, directly by measuring the heat produced in a chemical reaction. So that's thermochemistry. Then we talked about entropy. That was in chapter 4. And in chapter 4, we unified the idea of enthalpy and entropy by creating Gibbs free energy, delta G, which is equal to delta H minus T delta S. That's our expression for the Gibbs free energy of a chemical reaction. Then we started to examine the issue of chemical equilibrium, and we did that in chapter 5. And the idea of chemical equilibrium gave us the relationship between Gibbs free energy under standard conditions and Gibbs free energy under non-standard conditions. Namely, we could write that delta G under non-standard conditions was equal to delta G under standard conditions plus RT times log of the reaction quotient. And remember that we write that reaction quotient in terms of activities. So we have the activity of one of the products raised to its stoichiometric coefficient times the activity of the second product raised to its stoichiometric coefficient, divided by the activity of one reactant raised to its stoichiometric coefficient times the activity of the second reactant raised to its stoichiometric coefficient. And then we remembered that when that reaction proceeds, it proceeds forward as long as delta G is less than 0. Exactly the same principle as those electrons rolling downhill. Except in a chemical reaction, that reaction proceeds until delta G is equal to 0. And when delta G is equal to 0, we've reached equilibrium, which simply means that Q is equal to the equilibrium constant. Well, then I can take my expression for Gibbs free energy under non-standard conditions, and I can put in the condition of equilibrium. And the condition of equilibrium, first of all, is that delta G is equal to 0. So let me rewrite this. Delta G under non-standard conditions is delta G under standard conditions plus RT log Q. So if delta G is equal to 0, and if I'm at equilibrium, Q is equal to the equilibrium constant. And so I can then solve for my delta G under standard conditions, and that's equal to minus RT log K equilibrium. That connects equilibrium chemistry with Gibbs free energy. So that expression couples my delta G with my K equilibrium. Then along comes Michael Faraday in chapter 7, which we have just discussed. Michael Faraday gives us the profoundly important expression that delta G under standard conditions is the maximum amount of work that we can extract from that electrochemical cell, and that's equal to minus the number of moles times the Faraday constant times the cell voltage under standard conditions. That allows us to connect directly 3 completely different areas of chemistry: thermochemistry, equilibrium chemistry, and electrochemistry.